Okay, hi everyone, welcome back. So this is another data analysis video. So still focusing on like classical statistical analysis really, and the types of frequentist statistical tests that we usually encounter when we first learn in statistics and data analysis. So in the previous few videos, I've demonstrated how to conduct t-tests and how to do chi-square tests using Python, using different software libraries in Python. For the next few videos, though, what I'm gonna do is change track a little bit and cover data normalization, data standardization, dealing with outliers and data transformation. So other aspects of kind of data wrangling, which I don't think I really covered when I made a series of videos about kind of tidying up and cleaning data. So I thought I'd put these in here. It'd be kind of useful to cover these things at this point before moving on to some of the other null hypothesis significance tests, such as ANOVAs and regression analyses. It's kind of useful to know these things because they can be useful when you're doing those types of modeling techniques. So what I'm going to do in this video is talk about data normalization. You often will hear this referred to as feature scaling. Certainly in machine learning, it's commonly referred to as feature scaling. And it's important when we have variables that have been measured on very different scales. So we could have a data set that's got a number of different variables, and one of those variables could be measured in terms of, say, dollar amounts or something, and the other could be kind of some sort of measure of weight, and it could be weight measured in the hundreds of thousands of kilograms or pounds or something like that. So they could be on hugely different scales. And many statistical algorithms and machine learning algorithms struggle to process data when there are kind of large differences in the scale on which variables features are measured. So normalizing the data will not, so as this video, as it says, is about data normalization, but normalizing the data in this way will not transform our variables and make them normally distributed if the distribution of them deviates from normality. But it helps models such as linear regression and logistic regression. If we were to perform them, it helps them run better and produce better results. And it's also useful for us if we're looking at which variables might be significant predictors in a model. It can be sometimes hard to determine what's making a larger contribution. Because they're measured on different scales. It can look like one is making a large contribution, but it might be just the scale that it's measured on that makes it appear that way. Okay, so what I'm going to demonstrate in this video is a couple of methods for normalization scaling, and those are max absolute scaling and min max scaling. So I'm going to start with max absolute scaling, demonstrate how that works on an imported set of data, and then afterwards I will demonstrate min-max scaling. And min-max scaling is probably the most commonly used way of normalizing data used in machine learning. Okay, so right, let's start with max absolute scaling. So I'm going to import some software libraries and the data set, and then I'll explain what maximum absolute scaling is. So I'm going to import pandas as PD, seaborn as SNS, because I'm going to plot the distribution of some of the variables we're looking at, so you can see how the scale on which the variable is measured changes. I'm going to import numpy as NP. So the standard kind of nicknames, let's do that first, and then I'll say a little bit more about data normalization. So I'm going to import a data set called whitewine.csv. So it's a data set that's sort of you will find it used in a number of textbooks, and it's a record of of different variables measurements in relation to different types of wines. So I'm going to import this. I'm going to save it as an object called df for data frame, and I'm going to use the pd.read_csv method, and I'm just going to pass the name of the CSV that I've got saved on the laptop as a string. And there you can see, so it's a really big data set. There are 4,898 rows, so nearly 5,000 observations, and a number of different things are measured. So what I'm going to focus on is a couple of variables here. Free sulfur dioxide will be one, and alcohol will be the other, because they're measured on these variables have quite large scales. Okay, so let's have a look. If I use the data frame describe, df.describe on this, it will give us this kind of descriptive statistics of 8-number summary. And if we just look at the free sulfur dioxide variable, you can see that the scale on which it's measured is very large. There are like big differences between the min and the max value. So if we just look at that variable and we look at the min, so the minimum value on that is recorded for that variable is 2. The maximum is 289. Okay, so whatever scale that was measured on, that's kind of like it's on a scale, on a range between sort of probably about 0 and 300, which is a really big range. And you know, if we were including it in a model with stuff that's measured on a much smaller scale, it might create problems and might mean our model doesn't run as effectively as it could. So what I'm going to do here is I'm going to obtain a distribution plot. This might not work. If it doesn't, I'll just change the syntax. But what I've used here when I created this new notebook originally, I used the SNS Seaborn dist plot, D-I-S-T plot, and I'm just passing the variable df free sulfur dioxide to that. So if you've watched the videos I created on creating different plots and figures using Seaborn, the dist plot is now deprecated. It's no longer after certain versions of Seaborn it shouldn't actually work. So if this works, it will kick up an error telling me it's deprecated. If it doesn't work, I'll just change it. So dist plot, D-I-S-T-P-L-O-T, as a method was replaced by dist plot, D-I-S-P-L-O-T in Seaborn. Let's run that and see what happens. Okay, yeah, so we get this error, but it does actually produce a distribution plot that we were after. And so what it's done is it's created a histogram and it's overlaid a kernel density estimator on that for this free sulfur dioxide variable. And you can see it's measured on a scale from like 0 to 300. So the highest value recorded for this data is like 289 up here. But most of the values are between like 0 and probably about 75 even. Okay, so you know what we'd like to do is change the scale of this, and usually when you normalize data, you will change the scale it's measured on and say it on a scale between I guess it depends on the types of values you've got in your data, but you put it on a scale between like 0 and 1. And if you scale or a number of different features that are measured on different scales, it'll put them on scales between 0 and 1. Sometimes you can see, sometimes it will put them on a scale between -1 and +1. Most cases, I find data normalization, it scales the features on a scale between 0 and 1. The two methods I'm going to demonstrate here do that. So let me explain what max absolute scaling is. So the formula for it is, to get our scaled value, we basically take whatever our value is in our data set and we divide it by the maximum absolute value in the data. So what I'm saying here is we're scaling the data using the maximum value in the data set. So we're basically going to divide every observation by the maximum value of the variable in the data. So it's the maximum value in terms of the observations that we see. So in order to do this, what I'm going to do is I'm just going to make a copy of the data frame. I'm going to call it data frame df_temp. So I'm leaving the original df alone. Okay, and then I'm going to create a new scaled variable. So we're going to, using this copy of the data frame, the temp data frame, I'm going to use, I'm going to scale the free sulfur dioxide variable. And the way I'm doing that is basically just using this formula that I've shown here as a comment. So I'm taking the variable, each individual, and this will run through the vector, the array of values in that variable, and I'm going to divide it by that variable, the absolute value, the maximum absolute value. I think in this case, I mean, we're taking the absolute value, the maximum score. In this case, all the values are kind of positive, so we're taking the absolute version of it. Doesn't make much of a difference. But let me run that, and then I'm going to create that plot again. And what I'll do is, I kind of showed you the disk plot above it. It did work, but Seaborn or Jupyter Notebook doesn't like it. So what I'll do is I'll change it. So to create exactly the same plot, we could just use the diskplot method, and it will give us a histogram, but it will, we can also ask for KDE equals true. This should work. And if I run that, what we see now is, it looks slightly different to the one we got above, but what you can see now is our x-axis is on a scale from 0 to 1, okay, rather than 0 to 300. So we've changed the scale of the x-axis without actually changing the data in any significant way. So the distribution of the data is still the same. We can still use it for analysis. So let's do a different one. So the alcohol variable in this data set is also kind of recorded on quite a wide scale, I believe. So I'm going to change this and use the diskplot method, because that's the correct method to use these days. If I run that, so this is the original unscaled version. You can see it's kind of plotted on a scale. The distribution of values is between like 8 and 14. Okay, so that's a little bit weird. So we've got no values below 8 and none above, not many above 14 by the looks of it. So if we perform max absolute scaling on this, what that will do is kind of put this on a scale between 0 and 1 as well, like we just did with the above. So you can see here, so this is, I mean, this isn't like a really broad scale, I guess, between 8 and 14. It's a range of like 7, roughly about 7 values, and hugely different to the one above there with 0 and 300. But it'd be useful to put this on a similar scale as well and make it easier to comparison to make a comparison or to run a model that included both the free sulfur dioxide and alcohol variables. So I'm going to do the same thing as I did above. I'm just going to use the max absolute scaling formula to do this. So I'm going to use the temp data frame, and I'm going to basically take each of the values in the alcohol variable, and we're going to divide them by the absolute maximum absolute value. And I will change this again to use the new diskplot method. Alright, let me run that. And what we should see now is it's now on a scale between 0 and 1. So it's plotted this variable alcohol between 0 and 1, but the minimum value isn't 0. It starts at around 0.55. So it's kind of put the data points relative to the entire scale that it could be measured on. But if we wanted to put all values, so if we wanted to take our variable and set all values from a minimum value of 0, representing the smallest observation in our data, to a maximum value of 1, representing the largest observation in our data, so the actual data that's been recorded, not the kind of underlying scale, we'd have to do something called min-max scaling. So and also another note, if we've converted that, we changed the scale here, but if we wanted to get the kind of original values back, we can just use some algebra. We could basically our original, spelled wrong there, apologies, original value would be basically take each scaled value and multiply by the maximum value to do that. No, not sure why you'd probably want to do that. But you know, that is kind of one of the reasons why I like to save them as new variables when I change things. You know, if I scale a variable, so the original variable's intact. In this case, I didn't do that, but we created a copy of the data. So the original data frame with the original variables and scale is unchanged as such. All right, so let's look at min-max scaling. So this is kind of the most common, or what we call the kind of standard normalization technique that is used in machine learning to get machine learning algorithms to run quite efficiently, especially when they have huge amounts of data to process. So the formula for min-max scaling is simply your scale value is equal to whatever the value of the observation is minus the minimum observed value in the data, and then you divide that by the difference between the max and the min. So as an example, if our minimum value in our data set was 160, or on our variable was 160, the maximum was 200, what you would find is the minimum would map to 0 and the maximum would map to 1, essentially. So our data points would be between 0 and 1, essentially. And you can see how that works here. So if our minimum is 160, the smallest observation on this variable, then we would see, using that formula, 160 minus the minimum, which is also 160, divided by the maximum, which is 200, minus the minimum, which is 160. That gives us a calculation of like 0 over 40, which is just 0, essentially. And for the maximum, the opposite. So our maximum observation in this variable, say, was 200. So 200 minus 160 is 40, and then that's the same essentially as the denominator, which is the maximum of 200 minus the minimum of 160. So we get 40 divided by 40, which is just 1. Okay, so let's kind of do some min-max scaling. I'm going to create another copy of the original data frame. Leave those original variables unchanged, and we can perform min-max scaling manually just by coding this, essentially coding this particular formula. So what I'm going to do is take this new dftemp2 data frame object and just the alcohol variable, and then I'm going to take df2 temp alcohol, so each value, and I'm going to subtract from that, the second part of the numerator, subtract from that the minimum value. So this here will basically find the minimum value and subtract it from each data point observation. And then we're going to divide that by the maximum value minus the minimum value on that particular data frame, that particular variable. So let's run that. So I've done that. And if we can do the same thing, I will use the disk plot as it's the appropriate plot to use nowadays. The new plot has replaced the dist plot. So let's run that, and what we should see here is for that alcohol variable. I did it on the alcohol variable. Remember above here we did it, and we put it on a scale from 0 to 1, but the minimum recorded value, the observation of the data set, started about 0.55 here. Whereas now we've done min-max scaling, it's taken the smallest value in the data set is now represented by 0, and the largest is now represented by 1. So the shape and distribution is the same, but it's now kind of neatly mapped onto or scaled to between 0 and 1 for from the smallest observation, the smallest data point we have, to the largest data point we have. Okay, so hopefully that was useful. So that was data normalization, and when we normalize data, what we're doing essentially, just to recap, is we're taking variables that might be recorded on quite different scales, very different scales, measured on different scales, and we're kind of converting the scale of measurement that they're on, often to a scale between 0 and 1, so we can then, it makes it easier then to compare the influence of those variables and to get them to use them in some of the statistical models or machine learning models that we might be interested in. So the next in the next video, I'm gonna cover data standardization, which is slightly different to this, but it is another method of scaling features in some way. But yeah, doesn't like normalization. Is commonly used to put them on a scale between 0 and 1 or negative 1 and 1. Standardization doesn't do that. You're possibly familiar with it already through z-scores and things like that. But anyway, that's the next video. Hopefully this was useful, and thank you very much.